Hi, I'm Freya and today I'll be presenting my project titled Waste-to-Carbon Traceability in Radiology.
If we subside the contrast film and start sharing the digital images, it will help us a lot.
In this study, I traced carbon emissions generated from biomedical waste in a radiology department and identified the major contributors using the Pareto analysis and machine learning. The primary objective of this study is to identify the major contributors of biomedical waste using the Pareto analysis, followed by a machine learning model that predicts the carbon dioxide emissions. The data was collected from a hospital in Anand, Gujarat, after obtaining written permission strictly for research purposes. The study follows 5 key steps. First was data filtering and generation. Second was carbon emission computation. Third was Pareto analysis to identify the major contributors. Fourth was neural network modeling. And fifth was waste reduction planning. So our hypothesis basically states that less than 20% of waste items contribute to 80% or more of total carbon dioxide emissions. This is based on the Pareto principle, and if validated, controlling a small number of high-impact items can significantly reduce overall emissions. The analysis began with 16 files containing 63 biomedical waste items. 13 of these were biomedical waste files and 3 of these were film waste files generated from CT, MRI and X-rays. Since the raw files contained incompatible and inconsistent variables, we processed them through 6 structured steps. All 16 files were merged to generate a single master dataset which consisted of 587,648 datasets. Using this master file, we computed emissions, conducted Pareto analysis, applied neural network modeling, and developed mitigation strategies. Each record in the master dataset included investigation date, study name, item code and name, the quantity disposed, color category which is based on the bins, the waste type material, the item category, unit weight, emission factor, total waste, and total carbon dioxide emissions. The biomedical waste was classified according to the color-based bins. The red bin contained contaminated plastic waste, the yellow bin contained soiled and infectious waste, the blue bin contains glass waste, the white bin contains sharps, and the black bin contains general non-hazardous waste. So we physically measured the unit weight of each item and assigned them an emission factor. The total waste was calculated according to the quantity and the total carbon dioxide emission were calculated using total waste multiplied by the emission factor. This enabled conversion of every transaction into a measurable carbon footprint. Neural network modeling was used due to its suitability for capturing non-linear relationships in complex datasets. The output variable was carbon dioxide emissions, and the dataset was split into 70% training and 30% testing. The model performance was evaluated using the R-square and the errors were evaluated using the RMSE and MAE. The neural network uses all selected input variables to predict the carbon dioxide emissions, which is the output, and the model was trained on 70% of the dataset and validated using the remaining data. The results show that red and yellow bins are the primary contributors. These bins mainly contain plastic and soil waste. CT, MRI, and sonography procedures generate the highest waste volumes, and plastic emerged as the dominant contributing material. Item-level analysis revealed that contrast agents, films, and surgical consumables contribute significantly to emissions. These items are high in both frequency as well as mass. And out of the 63 total items, The top 20 were analyzed, and out of that, only 3 were responsible for the majority of emissions. This validates the Pareto hypothesis, and controlling these few high-impact items can substantially reduce total emissions. The waste generation increased steadily until January 2024, as shown by the graph, and after following implementation of mitigation measures, the waste level showed a decline towards 2026, indicating that the intervention was effective. Plastic and soil waste together account for nearly 99.8% of the total biomedical waste. Therefore, targeting plastic-based soil waste is critical for emission reduction. This shows the convergence graph, which shows 1700 training iterations, and an R-square value of 0.9867 indicates 98.67% prediction accuracy with minimal RMSE, demonstrating high model reliability. Based on these findings, we proposed a few solutions, including eliminating film printing, using washable linen sheets, installing glass bottle crushers, optimizing procedure kits, and centralizing oral contrast preparations. These measures will directly address the high-impact wastes.
We have started giving access to patients and doctors to our acquired images via digital platform called PACS system. This way we have reduced the consumption of our films up to 20% in just 1 month. This is directly we will be able to reduce our plastic and chemical waste.
In conclusion, we successfully traced biomedical waste to carbon emissions through structured data processing. The Pareto hypothesis was validated and a high-accuracy neural network model was developed. Practical interventions were proposed to reduce emissions in radiology departments, helping the environment. Thank you.